Well, thanks for the invitation to talk, and my subject does carry on somewhat from Tom's, but I need to begin a little bit earlier than Tom did, and just remind you that everything we know about the universe pretty much comes from the observation of electromagnetic radiation. So light, as we generally call it, but that means X-rays, radio waves, infrared, and so on and so forth. And we've got now, I think, as a result of the achievements in literally the last 12 months, to sort of just stand back a little bit and say, well, we've got a new tool to examine the universe in now, and I'm going to try and explain to you that tool, why it works and how it works. So basically, light comes from hot things. I mean, even infrared radiation coming from cold interstellar dust, that interstellar dust has got temperatures of 10 or 20 degrees Kelvin, and it's basically the thermal radiation from that which we're seeing when we look at these fantastic pictures from HST or these other magnificent telescopes. And this light travels from stars and galaxies to us, to our telescopes, through space, or I'm going to be correct about it and call it space-time, and so do gravity waves, but I need to begin gently converting you to a position where you really, really understand what gravitational waves are. Let's start with gravity itself. Obviously, this gentleman, Isaac Newton, played a very important role in our understanding of gravity, although there were people like Galileo before him who gave it a lot of thought. And he came up with this very simple formula, which I'm sure your students are all very well aware of, for the force between two masses, m1 and m2, separated by a distance r. And that simple formula, for nearly 150 years, was the sort of clockwork of the universe, because you could predict where the planets were, and indeed comets and other things moving around in the solar system, with an accuracy that was better than your ability to measure their position. So it seemed as though this formula really ran the universe and had incredible predictive powers. But by about 1845, people began to notice that the planet closest to the sun, Mercury, right in the center there, was in a secular way gradually moving away from the predictions. And Tom mentioned one idea as to why that might be, which was that there was a planet inside the orbit of Mercury that we couldn't see. But there were various other possibilities as to why the predictions of the position of Mercury weren't absolutely precise. It was stepping out of synchronism with the predictions, but only very slowly and by very small amounts. Well, 100 years ago last year, on November the 25th, 1915, Einstein submitted his final paper on the general theory of relativity. He'd had several goes before, and they'd been wrong in various ways. And he told people afterwards that it was in 1907 that he had his happiest thought. Now, I always think this just tells you what sad people we physicists are when you hear what his happiest thought was. But nonetheless, his happiest thought was that if somebody is in free fall, so if they jumped off the Eiffel Tower, while they're in free fall, they do not perceive their own weight. Okay, now, I must say, don't try this at home, don't get your school children trying it. But that was his happiest thought, and he realized that there was an interaction, there was something to do between gravitation and acceleration. That, when you were freely accelerating, you didn't feel the force of gravity. And that was actually a very profound and sort of deeply philosophical point of understanding. And Einstein always referred to this as his happiest thought. So if we go back to the Newtonian view of how the universe is constructed, how physics works, Newton felt that space was very well laid out, very orderly. If you wanted to measure the position of a particle, you had sort of straight lines telling you how far it was from this axis and how far it was from this axis. Everything very clear, orthogonal, everything at right angles, everything very predictable for space. And time was a completely different thing, nothing to do with space at all. That was Newton's position. But Einstein, following this thought and following his theory of general relativity, came up with the most extraordinary idea, the most extraordinary conjecture, you would call it. And that was that space is affected by the presence of matter. So Einstein's view of a coordinate grid like this was that if you had something very massive in the middle, something as massive as the sun, then the actual lines by which you make measurements would be curved, and hence your measurements would be affected by the presence of this mass. Now, it's difficult for us today because we've inherited so much of the language of space-time and curvature and warp factors and all these things. It's difficult for us really to appreciate how incredible this was as an idea. Remember, it came out in 1915. Again, in the middle of the First World War. It was an idea produced by a German, not good news as far as the British were concerned, a German Jew. Again, that raised all sorts of cultural issues which mitigated against this idea being easily accepted by people. It's terrible to have to say those things, but it was true. He proposed then, Einstein, that mass, or to be precise about it, the combination of mass and any energy that's in there provides a local curvature of space-time. So, as Tom's graphic showed very nicely, this curvature brings light from the same star or galaxy to us from an apparently different direction in space-time. So here you are in your garden with your little telescope, and you are looking at light which has been bent in this curved space-time, and you think the star is over there, but in reality the star's up here. So exactly as Tom's explanation of the eclipse experiment. That was a measurement extremely difficult to make, as Tom has shown you, in 1900. It's a very difficult measurement to make optically now, except that we see it every day in pictures of the Hubble Space Telescope. This is a picture of not a single object of great mass distorting space-time, but a group of objects. So these are very massive galaxies. They're grouped together in what we call a cluster of galaxies, and quite accidentally, behind these galaxies, there is another very distant, very blue galaxy. And because this is not a single spherical mass, as the Sun is, the distortion of space-time is a bit lumpy. It's a little bit like looking through the bottom. I can see from you that many of you will remember milk bottles, right? So if you look at the world through the bottom of a milk bottle, you see a distorted image. You see things several times. And what you can see in this HST image, a Hubble Space Telescope image, is this blue galaxy. There it is, there it is, there it is, there it is, here it is, here it is. There are many images, all of which have come through light being bent around this cluster of galaxies. So although the concept of space-time curvature, light deflection, is a difficult concept, there can be no doubt that it happens. We see it, as I say, every day in these kind of pictures. But what is curvature? The mathematics of curvature, I should change this slide really. The mathematics of curvature is very unfriendly, okay? You used to simple equations of this kind, the force between two masses, but what happened to describe curved space-time was that Einstein absolutely agonized with his friend Marcel Grossmann to find a form of mathematics that would enable him to describe this effect. It was not available to people easily at that moment. But this is what you get from Einstein. You can see it is very unfriendly, but this is the mass energy, this object here, T mu nu. These are just constants, gravitational constant, velocity of light. And then Einstein's curvature of space is a mixture of derivatives of tensors and all sorts of horrible things. We don't need to worry about that. But the essence of Einstein's idea is here, that the curvature of space-time is proportional to the mass energy. It's as simple as that. It's just very difficult writing down what the curvature of space-time is. But the concept is a very simple one. Well, I'd like you to come away with a clear idea of what gravitational waves are, and hence I need to sort of take you a little bit further into what it means to have a space-time that's curved. So if you just grip the side of your chairs pretty hard and stay with me. So in physics, very often we are measuring, aren't we, the separation between two objects. And they may be separated in the y direction and the x direction, and we need some way of finding their absolute separation from one to the other. And Pythagoras did this for us many, many years ago, and the separation squared is equal to y squared plus x squared, and I hope we're all agreed on that. I'm now going to write that in a slightly quirkish way, but I hope you'll understand that I'm not actually writing anything different. So I'm going to write this formula as s squared is equal to 1 times x, so that's that term, plus 1 times y, that's that term. And then I'm going to write down it's 0 times x times y, because there are no xy's up there, plus 0 times y times x. And the reason for writing that seemingly slightly pedantic and idiotic equation is that I want you to pay attention not to the x's and y's, but to these coefficients, 1, 1, 0, 0. And I'm going to write them in this form. And this, to somebody working in this field, is called the metric tensor. And I want you to sort of believe that this is exactly the world as Newton saw it. Extremely straightforward. You take 1 times the separation in x squared and 1 times the separation in y squared and nothing else, right? So you can see 1 times x squared, 1 times y squared, nothing times xy, and nothing times yx. So just writing that down tells you this is Newton's perfect orthogonal world with no funny curvatures or anything like that in it. And the nice thing about having established that pattern as a way of transmitting to you what this particular geometry is like is that if I now go from 2 dimensions to 3 dimensions, very easy, right? I don't have to go through any equations or anything. You can see immediately this is Newton's view of the world in 3 dimensions, and I could go on into other dimensions if we wish to. So how does this help us look for gravitational waves? Well, I've said that mass curves space-time, and the problem for many parts of the universe is that the curvature produced by mass is fine, but masses move around. This is a computer-generated picture. It's not an actual video, but of the galactic center. The cross there is the position of the big black hole, a few million solar masses in the center of gravity, in the center of the galaxy. And these are actual measured positions of stars going round it, and you can see that the world contains a lot of moving mass as well as stationary mass. So if mass curves space-time, but then the mass moves, what is going to happen to space-time? And what happens is that you get curvature of space-time, but changing as the masses move, and that is the ripple effect that are really gravitational waves. But let's go back to our Newtonian view of space-time and ask what would that space-time be like if gravitational waves were passing through it. And I've already told you the answer. It's like this. So now you can see you can instantly see this is not Newtonian space because you've got these funny bits in it. It's not 1, 1, 1 and all the rest are zeros. The coefficient governing x times x has got this oscillating term in it with an amplitude of h, and this one, the coefficient of y times y, has got an oscillating term with an amplitude of minus h. Notice the sign difference between them. Okay, so what happens when a gravitational wave goes directly into the screen is that those pluses and minuses mean that the measurements in the x direction, let's say x is along here, they are squeezed at the same time that the measurements in the y direction are extended. And then in the other phase of the wave, one is pulled out and the other one is squeezed. So you can see in this rather clunky picture that the gravitational wave coming in gives you a distortion of space-time, of your ability to measure things, and if it moves in one direction, it's moving out in the other direction. I've repeated the picture down here because this is a fractional effect. Okay? Now, if I say to you, I'm going to give you 1% of a certain amount of money, and it's going to be €1, you could get quite excited. If I told you it was €1 million, you'd be much more excited. So fractional effects get bigger the bigger object they're applied to. And you're seeing exactly that here. If you look at the actual motion of this part of the ship, it's sort of that size. This is a tiny ship, so the motion is much, much smaller. And that's an important effect that we need to come to. We use precisely that effect when we're trying to detect gravitational waves because we use the masses between which we're measuring, we separate them by large distances. And this is a picture taken from the air of the Advanced LIGO detector. And the vacuum tubes here, you can see them disappearing into the distance, are 4 kilometers long. So we want a percentage of something big to measure rather than the same percentage of something small to measure, because then the actual motion is much bigger. So the amplitude h is a fractional change in length, and we make it bigger by increasing the length, and we call this fractional change the strain. It's the same sense as the strain in Hooke's law is a strain. Well, how big are these strains that we might be looking for? Well, this is a picture of the amplitude or the strain, characteristic strain, as a function of frequency across, as you can see, a very wide frequency band. Start up here at 1 million oscillations a second, a million hertz, and we go down through 100 hertz, 10 to the minus 2 hertz, so that's one oscillation every 100 seconds, not 100 times a second, and then down to one oscillation a year and even one oscillation over longer periods than that. And what you can see here are the very roughly predicted sensitivity curves for the detectors I'm going to be talking about, LIGO and then Advanced LIGO, and here are some space-based detectors I'll say a little bit about at the end. I'm not going to discuss these detectors, there simply isn't time. But the frightening thing is not the frequency range. The frightening thing is the sort of strains that we're trying to measure. This is 10 to the minus 12, so that is 1 millionth of a millionth of the separation between the objects. This is 10 to the minus 18, so it's 1 millionth of a millionth of a millionth of the separation. And down here is 10 to the minus 24, 1 millionth of a millionth of a millionth of a millionth of the separation between the detectors. So we're talking here, if we have the two objects between which we're measuring the separation, if we have those separated by even 4 kilometers, you know, a millionth of a millionth of a millionth of a millionth of 4 kilometers is not very much at all. We're still talking about something like 10 to the minus 18 of a meter. And that's the sort of movement in and out that we expected to get when a gravitational wave came through the detector. Well, this is not the work, the LIGO detector is not the work of one institute, it's the work actually of 85, I think it's 85 different research groups in the world working very closely together. The two from the United Kingdom are Glasgow, who have led this work over a period of nearly 50 years, and my own group here at the University of Birmingham. But there are many, many people who've been involved in this, and we heard somebody talk about a contributor to the paper. There were 1,009 names on the paper. The actual names take up the first 3 pages of the paper. Scientists are very modest people, as you can see. So how does this detector work? How did this detector work? So let's go back again to measuring the separation between two objects as our means of detecting a gravitational wave. So we have 4 test masses here, one there, one there, one there, and one there. And these are big blocks, I'll show you a picture of them in a moment, big optical mirrors, and they are suspended on very, very fine suspensions, actually suspensions of glass, thin fibers of glass. And what happens is you have a laser beam It enters the instrument here, and then there's a beam splitter. So half the light goes that way, and half carries on through the mirror. The half that goes this way then bounces backwards and forwards between these two test masses, and the light that goes this way does the same over here. And you can see the reason for them being at right angles now, if the gravitational wave phase is such that these two masses are pulled apart, the other two will be pressed closer together, and so you'll get a phase difference in the light which comes out of these cavities. That light will pass through the beam splitter like that, will be reflected there, and will come to a focus on the photodetector. And so you set this whole thing up onto a dark fringe. You have a very substantial amount of laser power. 20 watts doesn't sound a lot, but when you remember it's bounced backwards and forwards many hundreds of times, the actual power in the laser field here is tens of kilowatts of laser power. So if you set this whole thing up on a dark fringe, so the outputs of the two arms are exactly cancelling, you only need a tiny twitch to start moving away from the dark fringe and bring light onto the photodetector. And that is how the gravitational waves are detected. It is big science. Here are the vacuum tubes. They're a couple of meters in diameter, and they run for 4 kilometers. The vacuum stations, huge pumping stations, huge laser preparation facilities. These are people working, you see, in highly clean environment, because if you get a kind of a bit of dust on one of these mirrors and it moves, it's going to change the light field, and you're going to think that is a signal from a gravitational wave. Here are the mirrors. They're some of the most perfect optics ever made, because, again, you want to combine these optical fields in such a way that they precisely cancel, and that will only happen if they are precisely flat fields. If there's any curvature in the optical field, you will never get a complete cancellation. Well, from about 2002 to 2006 or so, the instrument that we call LIGO was in operation. I didn't really explain to you, I'm sorry, but it's in North America. One unit is in the northwest of North America, in Washington State, at Hanford, and the other one is down in Louisiana, in the south east of the United States. So they're separated by about 2,000 kilometers, and the reason for that is that if somebody chops a tree down close to the instrument in Hanford, it will shake the mirrors, and you think, oh, gravitational wave, but that's unlikely to happen at the same time 2,000 kilometers away. So they're spaced particularly for that reason. Well, here are the sensitivity curves that were achieved gradually between 2002 and 2006. The green one is when it was first switched on, and you can see we got down to the ability to measure fractional changes of, let's say, 3 times 10 to the minus 21, but that wasn't good enough. And after tweaking it, we got down to the red curve, and then the blue curve, and finally the purple curve. And that ran very closely to this black curve, which was the theoretical prediction. So this is mostly funded by the National Science Federation in the NSF in the States, and they had been told that we could reach this black curve, and indeed, very closely, that was what was reached. However, for 5 years, no signals were found from stellar mass black hole collisions, which I'll describe in a second. And so this was a huge amount of money, a lot of effort gone into it, but nothing. There were very useful upper limits placed on various things, which kept us all slightly happy, but you know, at end of every week, you'd come in and your wife would say, well, you know, anything? I've done the shopping, I've done the iron, I've done... All right. We haven't discovered anything. Then it was decided to go for a factor of 10 increase in the amplitude sensitivity. Now, all this strain measurement is the amplitude of the wave, not the energy in the wave. So we deal with it rather differently from electromagnetism. So a factor of 10 in amplitude is a factor of 100 in the energy carried by the wave, but more than that, it gives you a factor 10 increase in your reception distance in the cosmos. And a factor of 10 increase, of course, these could be coming from any direction, so that's a factor of 1,000 increase in the volume that you could detect things within. So we detected none in 6 years, but by increasing the detection volume by a factor of 1,000, we could detect 1,000 times none. So I mean, it was not guaranteed that this would bring us what we needed. Here is the curve for Advanced LIGO, and you can see that we're a few times 10 to the minus 24. So we're nearly at a millionth of a millionth of a millionth of a millionth of the separation between these two test masses. And then on September the 14th, Advanced LIGO had been switched on just a few weeks before. It was a factor of a few more sensitive than LIGO, not fully the factor 10 yet, but a factor of 3 or so. On September the 14th, boing, there was an object on the screen, and this is what they saw. Here is the actual data, and you can see this oscillation, and this is the sort of fitted curve to it, which shows you it more clearly, but this oscillation getting higher and higher frequency, and then there's a bit of confusion, and then there's a higher oscillation that gradually dies away. And this is the picture from Hanford superimposed on the picture from Louisiana. And you can see that the two detections match extremely closely, even though the detectors are 2,000 miles apart, but you've actually got to time slide them together because the wave reached Louisiana 7 milliseconds after it went through Hanford because of the speed of light and 2,000 kilometers. And this graph is nice because it shows you the frequency of the wave, and it shows you this feature that the frequency goes whoop, like that at the end, and you may have heard people doing chirps, as they're called. This kind of curve is called a chirp. Well, this was extremely exciting. What we think happened, what we believe happened, was that there were two black holes in orbit around one another, a very common situation in the universe. And as they're in orbit, they're actually radiating gravitational waves because they are curving space-time backwards and forwards, and that takes energy to do that. And space-time is extremely stiff. The reason why I'm sort of not being pulled very strongly towards the computer over there is because space-time is very stiff. The computer over there is not curving space-time very much here. It did a little bit, but not very much. And so you need an enormous amount of energy to curve space-time and produce these ripples in it. And that energy has to come from somewhere. It comes from the orbital motion of the two black holes. And so gradually they're getting closer together because the orbital motion is losing energy. And you can sort of see that graphically here. But then there comes a point where they're so close that they touch. There's a merger, which is very complicated. And that's why there's this sort of messy stuff here. And then there's what we call the ring down, which is you've got this bigger black hole. It's not a perfect sphere because it's just had two black holes joined together, and it sort of wobbles, like a plate of jelly until it gets to be completely spherical. And so those are the explanations for this signal. And by fitting the theoretical curves to the data, we can produce really astonishing accuracy measurements of, for instance, the mass of one of them was 29 solar masses. The mass of the other was 36 solar masses. We can tell where the spin axis of the two stars were pointed because that changes slightly the curves that are observed. We can tell very roughly where it was in the sky. We're not taking a picture of anything here. We're just having masses move around, and we can say, well, it didn't come from over there, but it might have come from over there. And interestingly, we can measure the distance away that this event actually originated. Well, the distance is an interesting thing because in most astronomical observations, you can't measure the distance by just taking a simple measurement like that. You have to do other things. And the reason we can do that is because the orbital period and the rate of change of the orbital period, remember I showed you it speeded up when it got close to the merger, they're related by this equation. Here's the change of the orbital period, here's the orbital period. So if you can measure these two separately, then you can determine, these are all constants, you can determine the total mass of the system. And if you know the total mass of the system, then you can predict the amplitude. You can predict this little strain amplitude of h. Now, of course, that prediction has got a distance factor in it. So you know the period, you know the mass, you know h, and you can work out how far away it is. But you've got to measure two things, you see. You've got to measure the actual period of the binary orbit and the rate at which it's changing, dp by dt. If you've got the two of them, you've got two equations with two unknowns, m1 and m2. You can solve for m1 and m2, and then you can put it into the equation that tells you exactly the amplitude of the signal you might expect at a certain distance. Compare it to the amplitude you measure, and you can tell how far away it is. The remnant black hole, this is the thing that really gave me the most enormous buzz. The remnant black hole has got a mass of 62 solar masses. Now, those of you who are really good at mathematics know that 29 plus 36 is not 62. All right. 3 solar masses disappeared in this merger. They're gone. They've dissipated in ripples in space-time. I find that absolutely extraordinary. Well, it's not extraordinary. It's exactly what we knew was going to happen. But when you bloody see it happen, you think, wow, it's incredible. But I think this, for me, was the really extraordinary moment. It's true, you know, actually gravitational waves carry energy, and in 0.2 of a second, we saw 3 times the mass of the sun in energy disappear. Gone like that. So this is quite surprising astronomy with some quite surprising accuracies involved. Well, these were stellar-sized black holes. They were 20 or 30 times the mass of our sun. Those are slightly unusual stars because the majority of stars actually are, you know, 1 or 2 times the mass of our sun. But there are much bigger ones, and I've hinted at that already. This is an X-ray picture, actually, of a galaxy, and you can see 2 lumps in the middle, 2 bright patches in the middle. And we think probably those are 2 supermassive black holes, masses perhaps 100 million times the mass of our sun. And there are 2 there because this is the result. This galaxy is a result of 2 galaxies merging. And so they each had a black hole at their center. As they came together, the black holes have started going round one another. But black holes that are 1 million times the mass of our sun go round much more slowly than black holes that are 10 times the mass of our sun. So for that reason, we need to be working in the future now at frequencies much lower than these frequencies that we detected the signal before. Those frequencies were something like 100 or 500 hertz, so it's a frequency of pianos. We need to be working at frequencies of 10 to the minus 2, 10 to the minus 3, so that's 1 oscillation of the gravitational wave every 15 minutes, so a very gentle oscillation period. And in order to do that, we're going to have to move our detectors to space. We're still going to need to put a large separation between the test masses and measure their separations, but now the separation has got to be rather large. What we expect to see is similar sort of events, binary motions getting faster and faster, and then there's a merger and a splash of radiation, but now from black holes with a mass of 10 million solar masses or that's 1 million solar masses, and we expect their radiation to be at these kind of strains, so really quite high, and then we'll get a blip and then they will disappear like that. So this will be the largest instrument ever. It's called LISA. It doesn't exist yet, but it's in planning at the European Space Agency, and we want to have 3 spacecraft separated now by 5 million kilometers, so there's obviously no possibility of doing this on Earth. And these 3 spacecraft are not in orbit around the Earth, but they're actually in orbit around the Sun, but they're following behind the Earth. And the principle is much the same as for LIGO, that you have lasers which measure the separation between these, and when a gravitational wave goes in perpendicular to the plane, you know, one set of them stretch out and the other stretch in, and then in the other phase of the wave, the other things happen. The pattern rotates once a year. They go around the Sun once a year, and so we can scan out the sky and get perhaps better position measurements than we have with LIGO. And this is the sort of artist's impression, the spacecraft. And inside the spacecraft, there will be a test mass, and it's between those test masses that we're measuring the separation. The spacecraft is just there to protect the test mass from the solar wind and various other things. I've already said that. But we need to measure now the separation between these test masses to 10 picometers over 5 million kilometers. So that's not entirely straightforward, but being arrogant buggers, we believe we can do it. It'll have very sophisticated telescopes on each spacecraft, preparing the laser beam. Here's the test mass in its box, and the laser beam will shine on that, and then it will go out to the other spacecraft, and you'll compare the phase with the beam coming in. And because you don't get, I mean, this is a $1 billion, $1.5 billion kind of experiment, and you don't get money to do that unless you're absolutely sure you've got the technology. So very fortunate we've been given money by the European Space Agency to build a smaller version of this, very much smaller. It was launched in November last year. Here's the spacecraft. These are propellant tanks. And we're testing our ability to measure the test mass separation to this level of 10 picometers. Here are the two test masses. They're not 5 million kilometers apart. They're 43 centimeters apart. But that doesn't matter. We're just showing that we can measure to that precision. If we can do it in 43 centimeters, we can do it over 5 million kilometers. And the results from this have been absolutely spectacular. It's worked brilliantly from the word go. We were supposed to achieve this again. It's the same, sorry, it's rather blurred, but this is strain sensitivity versus frequency. We were supposed to achieve this. The LISA mission is supposed to achieve this, and we actually achieved this blue line here. So we've already demonstrated that we can make these measurements sufficiently accurately. I'll skip over that. So the implications are that we can now study black holes in detail. I mean, it's extraordinary to come here and say, it was 29 solar masses. You know, for astronomers, that is precision for these kind of objects that's unheard of. We've got further evidence that Einstein's picture of gravity, however bizarre it may seem, is basically correct. I was amused by, Tom's gone now, but I was amused by his picture of Einstein and Sir Arthur Eddington sitting next to one another. Some of you may know that the mathematics of general relativity is so obscure and abstruse that a press reporter asked Eddington, when the announcement of the 1919 eclipse was made, he said, excuse me, Sir Arthur, is it true that only 3 people in the world understand general relativity? And Eddington said, who's the third? So it was an obscure language it was written in, and we now know that however obscure that language was, it's right to at least the precision that we can measure. We've got yet another example of the effectiveness of large international collaborations, and any country that cuts itself off from close collaboration with neighbouring countries is going down a very dangerous path. A new window on the universe has been opened. I hope I've convinced you of that. We'll be able to study not just the hot parts, but the parts that are moving violently. One of the long-term goals is to actually measure the gravitational waves from the Big Bang itself. Now, light, here's the Earth now, here's the Big Bang. Light, photons, come from a period 100,000 years, or a few 100,000 years after the Big Bang. If we could measure astronomical neutrinos, they would come from a period 1 second after the Big Bang. But gravitational waves come right from the Big Bang itself. They're not scattered or absorbed by anything else. So if we could measure those, we would be listening, literally listening to the Big Bang, which is quite an extraordinary thing. Right, so what to look out in the future for the news. As you see, I've given this talk through the years, and I've got some tick marks now, which is really very nice. Launch of LISA Pathfinder, results from that. Announcements from Advanced LIGO. There will be further announcements. We're detecting events at the rate of, well, we don't quite know yet, but let's say between 3 and 10 a year, I think is probably the expectation at the moment. I haven't mentioned the very low frequency measurements. You can use the Earth and a radio pulsar as the 2 test masses, and use the regular pulsar signal as the laser beam between the two, and detect gravitational waves that way. The other thing is that you can use the cosmic background and look for patterns in it, which really are the pattern of the gravitational waves when this cosmic microwave background was formed. That hasn't been successful yet, but there are other ways of measuring gravitational waves. The last thing I would say is that there is something really important to look out for in the news, and that is progress in uniting general relativity and quantum mechanics, because these are the two intellectual pinnacles of the 20th century, each of them tested individually and internally consistent, but yet when you bring them together, they kind of blow up in your face. They're completely inconsistent. So one thing to look out for, and I guess I'm looking at the younger members of the audience here, progress in understanding how those two theories work together is going to bring not just more exciting results in astronomy, but I think more exciting technologies and all sorts of things may flow from that. So that's something, again, to look out for in the news. But thank you for listening.